So welcome to the Silicon Valley Ethereum meetup. So we're very happy to have Joachim Breitner, hopefully that's at least close enough, speak to us on some lattice attacks on Ethereum and other ECDSA-based cryptocurrencies, including, say, HTTPS and SSH, I think. So I will also give an introduction to lattices.
Thank you. Yeah, welcome. Thanks for the invitation to speak here. I'm based in Germany, so I was in town by accident, more or less, because of this blockchain thing next week. So I thought, nice opportunity to talk about some research I did. These days I work for Dfinity, but what I'm presenting right now basically is work that has happened while I was still a postdoc at Penn in Philadelphia, where I also met Nadia and collaborated with her on that work. So this is, yeah, I guess my personal interest, not my work interest. But you can also talk to me about Dfinity-related stuff afterwards if you want. I'm not undercover or anything. All right, so you might have heard about the law of large numbers. So if you do something very often, then on average you kind of reach the middle. There's an adage that is like a variation of that, the law of truly large numbers, which says if you have a very large sample size, it's not talking about what's happening in the expected case, but if you have a very large sample size, then even the most unlikely looking thing is going to happen. You know, like a 1 in a million chance happens 10 to 10 people in New York every day. And then Nadia conjectured that there's a cryptographic variant of that, saying that if you have enough independent implementation of crypto, then even the most stupid, outrageous things will happen, and you will find that. And that's basically how she finances her research group. She looks for people screwing up and writes papers about it. And that's what we did here. So more math background, but I guess we'll have some of that. You might know that most common blockchains, including Ethereum and Bitcoin, use the ECDSA signature scheme as the fundamental building block for how you sign something. And in order to see how the tech works, you have to look a little bit how this scheme works. If some of this is too mathematical for some of you, that's fine. I will try to point out the slide where you can join back in and pop up the level again. But for those who are into the thing, we'll have a look. So we have an elliptic curve. It was already mentioned just a minute ago. It's essentially a group with meaning you have points on this group, and you can multiply them with a number. That's the basic operation we need. There's one particular point. Yeah, this doesn't work with. I'll use. Yeah, I'll do that pointer. So there's a particular point on the group. It's called a generator. We call it G, and it's basically a parameter of the whole signature scheme. So for Ethereum, there's one group that everybody uses, and they all use the same generator. And n is the order of the generator. So if you multiply G n times, then you end up with 0. Now, when you want to do a signature, you need a private key and a public key. The private key is just a simple number. And you can take your birthday if you want, but that would be stupid. But it would work. And then from the private key, you can calculate the public key just by taking the generator and multiplying it d times, where d is your private key. And it might look like it's very easy to calculate d if you have this q, this public key, because you just divide by g. But this, just dividing by g, is precisely what's hard in elliptic curves. This is what you always hear as the discrete log. If this were easy, then the whole crypto stuff wouldn't work. But it's hard. So if I give you q, even though you know g, you don't know d. Okay, this is your private key and public key, and then you want to do a signature. So first you take your message or your transaction, and you create a hash from it, just to boil it down to a simple number. So we have the hash h. And now comes a catch. For the ECDSA or DSA in general, signature schemes, you also need a nonce. We call it k, it's just another number. And usually you pick that at random. And it's very important that you pick it right, and we'll come to that. You get this number k out of whatever you want, and then you do a little bit of math. So you do one elliptic curve multiplication. You multiply k times g, and you see it's actually almost the same thing that you did with your private keys. So you can think of k as a second key that you're using, but you're only using it once for this particular signature. And then the signature consists of two components. One is r, which is basically k times g, but you only need the x component. This is this notation. And then there's the component s of the signature, where all the other stuff goes in particular the message hash and your private key. And there is no more lattice stuff. No more elliptic curve stuff. That's just regular integer arithmetic modulo n. This is textbook level signature, and you can implement and play around with it. You can play around with it. Don't implement it. So what can go wrong? So the first thing that can go wrong is you tell somebody k. That's bad, because if somebody has k and then they have the signature, so they have r and s, they also know n because it's a parameter of the whole curve, so it's public. They can put this all in this equation and they solve for d, and bam, they got your private key. And remember, on Ethereum or Bitcoin, if somebody has your private key, they have all your money. At least all the money that you put in on the blockchain. Maybe better not all of it. So keep k secret. Okay, that's not too hard. Next pitfall is you have to use a fresh k every time. If you only once, for some reason, use the same key, same nonce k in two different signatures, then you can do a little bit of more math. But basically, you subtract these two signatures from each other and the hashes, and you do some more math, and you get k. And we just learned when we have k, we can also get d, the private key. So if you ever use the same nonce twice, bam, your money is gone. And this happens a lot, or this happens in the world, I should say. A lot is relative. And now, but this is nothing new. A bit more intricate is the third one, and this is like the main focus of our work here. You have to pick k properly at random. So k should be a number between like a 256-bit number. And if you pick k randomly, but maybe too small, so you only have always have a 64-bit number. I mean, 64-bit sounds a lot, but it's still much smaller than 256-bit. Then there's some math we can do, where if you use different but small nonces for a number of signatures, then we can basically, just like we did some linear algebra down here, and linear arithmetic down here, we can create a system of equations, and then we throw this into the machinery that Chris just showed us, and out comes k. And because k comes out, also d comes out. Yeah.
So the nonce is something that the signer generates at signing time. So
yes.
if I'm signing,
Yeah.
Okay.
Yeah.
And then it gets destroyed. Like,
Yeah. You immediately forget about it afterwards, and better don't store it anywhere. Right. So not only you have to get the k. It not only has to be a different one every time, but you really have to take it from the whole space of all possible k's. And there's a scary lattice section, but maybe I'll skip that and try to give a high-level intuition of what's happening there. So, if you remember your high school or college math, then linear algebra was what you used to solve linear equations. Linear equations always had the form, you had some unknown, and then some additions or subtractions, and more unknowns with coefficients, maybe some coefficients on their own, and you were solving them, and like that is equation. And you could try to solve it by hand, by thinking a lot, but it was hard. So the easy way to do it was like to put in a matrix and throw matrix inversion at it, like some standard linear algebra tools. So this is almost what we have here. The difference is that in linear algebra, you can get numbers like solutions that are like a third, like or 0.25 somewhere in the vector. And this doesn't make sense here, because we know that, of course, your secret key and the nonces, they are integer numbers. And that's precisely what lattices give us. So lattices give us similar tools that as linear algebra, only that they will always find integer solutions. And Yeah, and that's like, I must admit that I'm myself not an expert in lattices, like this, all the lattice math stuff was in Nadia, so this is roughly my knowledge level about lattices, but so we're all on one boat here. But for that to be solvable, it's important that the k has to be small. Like lattice, the k, which means the nonce that you are using, if it's small, meaning you use a few number of bits. And why is that? And just for intuition, we just learned that lattices have this shortest vector algorithm, where you build a lattice and you find a very short vector. And the vector that we are going to find is the vector full of these nonces. And if the real nonces are like large, then it might be anywhere in the lattice, and finding a short vector doesn't really help you. But if you assume that all the nonces are small, and the lattice tool will give you a small vector, then with a very high probability, this vector will just contain the real nonces. So maybe that's the right level of math. If somebody wants, yeah.
And that applies, I would assume, even if 256 bits and are small, even if the space, it doesn't really matter. Like if the size of the case are small, even if you have potential of 2 to the 256, you still have the same problem.
Yeah, yeah. So all the curve that is actually being used in Bitcoin and Ethereum uses 256-bit numbers for like all the keys and nonces, which is a pretty big number. So as long as you only use like 64 bits or less, like we'll see in a moment what the then this will work, and it will work pretty reliable. Yeah.
So is it a fair intuition to say that the hazard of this attack is in some sense proportional to the number of bits of actual entropy there is in the
yes
constellation?
That's precisely this slide. So if your random number generator produces nonces that are only 100 up to 128 bits, so you only use half the bit space, then 2 signatures will reveal your key. If you use 248 bits, so you basically use everything but the highest byte of your random number, then you need 40 signatures, but the 40 signatures using the same key and nonces that have this property will reveal your private key. If you use 256 bits for the nonces, like you should, then this number, if you want to, like the number of samples, eventually goes like up exponentially. So that means this doesn't work if you do it properly. But even like, so okay, there are basically 2 main attacks that aim that. There's the lattice-based one, and there's one involving Fourier analysis that we didn't use for this paper, for this work. The Fourier analysis work can even recover the private key even if there's a single bit missing in your randomness, if you have a lot of signatures. So this is like lots of signatures, good for very small biases. What we do here is that we have large biases, but a very small number of signatures. Okay, so that was the scary lattice section. And this is again a summary of what we say. If your nonces, so this is the space of like the bits that you could fill with your random number. If you only fill up to here, then 2 subsignatures, and we can throw lattice magic at it, and we get your private key. You're screwed if you use small nonces where like the top bytes or bits are zeros. But more than that, what if the high bits or bytes of your nonces are not 0, but they're all the same? Then it's not a small nonce because it's a big number, but they're like very close to each other. And then you can just subtract 2 of them, and then by subtracting them, all these data here goes away, and we're again in this case. So you're also screwed if your numbers have a fixed prefix. And even if it's a fixed suffix, so maybe for some reason the lower bits and bytes of your nonces are not randomly chosen, then we can multiply this whole thing, and also the signatures, and shift basically the random part to the end, and then we're in this case. So there are a bunch of variations we can look for. So this is what we want to find. So now the question is, does this happen in the wild? And to answer that question, we have to somehow get a hold on a large corpus of signatures, possibly created by many different people, some of them crypto enthusiasts, but maybe not too professional. So blockchains. Yeah.
It sounds like you're saying, right, that even if someone generated truly randomly, but like a few thousand signatures, right, then you would get 40 signatures with only like 200. So does that mean that maybe a few thousand signatures?
No, because for that I would have to know which one of these many thousand signatures I have to select to pick the 40 one, and that's again like a very low probability. Like if I just take random 4 signatures from your 1000, the likelihood that these 40 happen to be all the small K's is very low.
You have to feed the correct 40 to
your... like if I'll throw signatures into the box, but if there's one signature in there that has a large K, it just doesn't work.
Obviously, because you don't know the K's beforehand, you wouldn't know how to pick them. So
yeah.
You have to make an enormous amount of tries. It goes up really exponentially with the number of...
Precisely. And then that's where the security of the scheme is, and if you use it properly, like you can't that easily break it if you use proper randomness. Okay, so what do you do? Oh, I guess first the background. So all the big blockchains, Ethereum, Bitcoin, Ripple, use the same elliptic curve, SEC P256K1. Some people say it's an odd choice because it's like not a very common curve outside that space, but I guess that's what Bitcoin shows. And then what happens here is that when you want to do a transaction on Bitcoin, you take the transaction, you get a hash of the transaction, you sign that, and then you put it on a blockchain. And interestingly, the address that you use in Bitcoin, like you know the addresses, it's not directly the public key. Like you would expect that I'm sending money to some public key, but really it's the hash of the public key. And that's not really relevant for most people, but for us it's kind of annoying, like for us if you want to break crypto, because that means we don't get our hands on the real public key to look at it until somebody actually does a transaction using that key. That means until money flows out of an account. So for all the Bitcoin accounts where only money went into, and it's not the accounts technically, it's like unspent transactions, but you know what I mean. Anything that only received money, the public key hasn't been revealed yet. But anything where a single transaction goes out, we at least find the public key. And we find the signature. Okay, so what we do, we download the corresponding clients, we sync the blockchain, and we extract the signatures. This part sounds easy, but there was actually a significant amount of engineering involved. Especially for Bitcoin, calculating the transaction hash is quite a complicated procedure. So it was like, didn't feel like I wanted to implement that and maybe get it wrong and stuff. So the easiest way of getting our hands on the raw data was to actually take the Bitcoin client, patch it, so whenever it does a signature somewhere deep down inside the code, it would just write it down on the side in a file. And then I downloaded the whole chain and said, please revalidate. So I went through all signatures in the Bitcoin blockchain and checked all the signatures, and as it was doing that, wrote out like the things we cared. The hash of the data, the public key, and then the transaction ID to trace it back. For Ethereum, Ripple, it was a bit easier. The API provides the hash directly, so we could get that. For Ethereum, we ran a local node and then extracted the data using RPC, and for Ripple, we were even more lazy. We just used the public node and downloaded all the data. Okay, so this was our plan. We scrape the blockchains, we get 1 billion signatures, that's a large number. We group them by public keys, so we have 60 million public keys to look at. And then we looked for these 2 pitfalls. Did somebody use the same nonce twice? And did people use biased nonces? And then we ran this on Nadia's cluster, 50 CPU years, and then we looked at the private keys that we extracted this way, and whether there was money in them. And then we checked, are we rich now? And then if we're rich, we retire. And if we're not rich, we buy the paper. So we wrote the paper.
Excuse me.
Yes.
Did you consider doing this computation, 50 CPUs, using algorithms, what is called gates, for quantum computer or You were not considering this at all?
No, we had to use
Okay.
the cluster that we had.
Okay.
And I don't think quantum computers are practically that fast yet.
Oh, they are not far. But the question, what you want to really to protect.
Right. No, Nadia has a nice cluster in her group, so we use that.
Okay.
Okay, so let's look at what we found. So we didn't find a lot of money. We didn't find money. We didn't steal it. It wasn't worth it. It was more fun writing paper. So this is repeated nonces. So signatures where there are multiple signatures of one public or one key that use the same nonce. And this is not very new. People have studied this on Bitcoin many times already. So there were like 2.5 million signatures that repeated the nonce, 1,300 keys. And it's known that people check for that. So there are people who are actively monitoring Bitcoin, and whenever they see a signature that uses a nonce that has been used before, they steal the private key, and if that key has money, they take the money. For Ethereum, there were 3 keys that had repeated nonces, but I think actually most of these signatures were like small numbers that people created, but looked like handcrafted signatures from people playing around with it. And for Ripple, there was 1 key that we could extract, and it actually had 30 Ripple X, whatever it's called. So that's like 2 pizzas or something. So it looks like nobody's yet looking at Ripple to extract these funds from these bad implementations. Yeah.
And the way they know that the nonce has been reused is because the hash is the same, repeats?
Not the hash of the public key.
How do they know that?
It's very simple, because if you look at the equation for the signature, then the R value, which is really just the 2 components of the signature, one is R, is just the nonce times G.
Okay.
And so you immediately check see that.
It will be constant across it.
Yeah, you'll see 2 signatures that have the same bytes
Okay.
in this field. It's very simple to check for. Right, a bit more interest. I get to some of. I'll make some hypothesis about what happened here in a moment, but let's first go through the results. For the biased nonces, which is the kind of new observation that we did, we also found some. We found a bunch of varieties. So some had a fixed prefix and then 64-bit of randomness. Some had 108 bits random and then followed by a fixed suffix. And then we had a bunch of small nonces and a big cluster of 64-bit nonces. The star means these were used in multi-signature addresses. So just to recap, multi-signature addresses in Bitcoin are addresses that, in order to spend money from them, you have to sign the transaction with, let's say, 2 out of 5 keys. And I guess it's if people share an account, or if you want to have access to security and you put 1 key in some cold storage, then that might be useful. And it's noticeable that especially this large amount of signatures here were all multi-signature transactions. By the way, the size of the circle, if you haven't figured out yet, is the number of signatures from that time that we could break.
Well, why do you think that is? That the multi-signatures had bad nonsense?
Good question. Well, we'll come to that. So this was like the second step. We collected the results, and now it was now the sleuthing began. So like trying to figure out what happened here, because okay, we knew when these signatures were made, we knew the transaction ID, but that doesn't really tell you much, at least in Bitcoin. Some other account, then money went from one account to another account. So we really tried to find out what implementation has these faults. Why are these strange patterns here to find? And we can't explain everything, but we found a few things that shed some light into what can go wrong here. So the first one actually isn't a fault, it's an intentional abuse of the system, I could say. So among the repeated nonces, there was this, many of them are actually the same value. This is this n minus 1 over half, or if you write it down as a number, this nonce value. So why is this interesting? This number is, if you take the order of the group, like the size of the elliptic curve, you take -1, you divide it by 2, and this is this number. And if you use this number as the nonce in your signature, then the R value that you put in the signature, which is like bytes that you have to write in the transaction that you put on the blockchain, happens to be short. It's 166 bits instead of the usual 256 bits. And if you have a shorter signature, it means your transaction is shorter. You save 11 bytes, and that means you're saving on fees. So you can choose to use an unsafe signature scheme, but then pay less for your transaction. Maybe a bad trade-off in most cases, but there's this thing, supposedly, and I assume people in this audience know more about this than I do, but as far as I know, you have your Bitcoin accounts, and often they end up with like very small fractions of Bitcoins left from stuff you were doing, and then you want to clear them out and collect the dust, so to say. And for doing a very small transaction, it's very useful to not have to spend a lot on fees. Like it's pointless to collect the dust if the collecting of the dust costs more than there's money in these transactions. So you can use this trick and save some money. And because the account is empty anyway, and if you expect no more money to come into it, then revealing the private key this way is not a problem. So far for the Bitcoin side of this story. The real mystery here, to at least the crypto people, as in cryptology, why does this curve has this property? It's not at all clear that if you take the generator and you take half of it, that it should have that should be short. And it's not only in this curve; it's also in the other SecP curves that have this property, and they all seem to be derived from the same 160-bit number in a non-obvious way derived. So maybe somebody used a SHA-1 hash, which is reasonable for the 90s when they created these curves. Creating means picking the parameters of the curve. But it's not documented in the standards. So it's kind of fishy. And you'll be building the whole blockchain here on cryptography, and it's not completely clear how these parameters are chosen and what the reasoning behind it. So I don't want to get anyone excited here. There's no reason at the moment to believe that this in any way affects the security of the system. So far it's just odd. And if anybody happens to know more about what happened in the 90s there, we're happy to hear about it. It's still not completely solved how these parameters were chosen and why they have this property, and why G over 2 has this property and not G itself. Alright, so far for the weird trick. The rest is really just people screwing up. So one screw up is, of course, human factors. People screw up. So one compromise key of using repeated nonces, we could trace back to a signature that is part of a 3 out of 5 multi-sig address. So it's one of the keys that you need if 3 of the keys to spend some of the money. And this address actually has quite a lot of money in there. It's $170,000 at the moment. And it's the address to collect donations for darkwallet.is. Some wallet, I think it actually defunct these days, but this was like some years ago, some wallet project. So we contacted the author, and he said that, oh, maybe it was me, I was doing some signatures by hand. So if you do signatures by hand, maybe don't do that with keys that hold several $1,000. In this case, now it's effectively a 2 out of 5 multi-sig address, so you still need 2 other signatures, and it doesn't affect the security of that thing fundamentally, but still, don't write signatures by hand if you're dealing with a key that is valuable. We found some very small nonces, and these obviously are just people playing around with the system and picking some k values by hand. So I assume that somebody who uses 1 or lead as the nonce are not writing production code or dealing with real data. But it's still nice to find these things there and know that there are geeks out there that leave little signs. I don't know what that number should be. It's probably not Probably not important. Right. Then a bit more serious, and it's still repeated nonsense, are cases where the random number generator just fails. And two of the most widely covered incidents were, first there was this Android bug, where Android wouldn't provide, or if you use the Android random number generator wrongly, I think you have to, if you fork the process, then both forks continue with the same seed, so they both get the same random numbers. You may end up picking the same random number for two different signatures, and as we've seen before, that kills your private key. And this has actually caused lots of people who are using wallets in Android to lose, which is unfortunate. And a similar incident happened with the wallet on blockchain.info, which was fetching its randomness from a service called random.org. It's basically randomness as a service. You make a request and it gives you a new random number. It's very convenient if you don't have random numbers yourself. But then random.org changed the system so that it would redirect HTTP to HTTPS. It's laudable. It should encrypt all communication. It's good. But the HTTP client on the blockchain side wouldn't follow the redirect. It would just take the response, which is, please go to HTTPS, and take it as a random number. So for a while, every signature from this wallet was using the same key, and people lost the money. This doesn't explain all the repeats that we see here. So there must be more stuff going on, but we don't have any more insights here. Okay, let's get to this big chunk here. This was fun to discover. Greg Maxwell, supposedly a famous name in the world, in the Bitcoin world, helped us a little bit here finding this. So for 1 year, there's a large number of not repeated nonces, so they were freshly chosen, but they were random, but they were only very short, only 64 bits instead of the full 256 bits. And for some reason, Greg had a rough idea what project could be involved here, so we could trace the history of this bug on GitHub. And it was a project by BitPay, which is a company in the blockchain space, and they produced a JavaScript library called Bitcore, which just implements lots of Bitcoin-related functionality. And in July 2014, they, I guess, switched the implementation of the big num, so working with large numbers often needs a separate library. So they were switching to some other library, likely called elliptic, and in that commit, there's this line where they pick a new random nonce. And it's using secure random, some module, with the method getRandomBuffer, so it's filling a buffer, area of bytes, with randomness, and the buffer has size 8. Well, 8 byte, 64 bits, is less than the full 256 bit. Unclear how this 8 ended up here, but it was there, it was committed to master, it was released in July. It was noticed very shortly after. So just a month later, somebody else in that project noticed, oh, stupid, this K should be 32 bits. And they made this very small change, they released it a month later, but between 0.128 and 0.135, that's 7 releases that went out. And by the nature of the ecosystem of JavaScript using projects, I guess they just pin versions and then don't upgrade promptly, or they copy the whole dependency into their source tree, vendor dependencies. So it looked like for a whole year, this bug was still present in other tools and projects that were using this library. And it looked like some project that was particularly involved with creating multi-sig signatures. So this is a very educational lesson about how our software ecosystem is not where it should be. Like, these things should be fixed. Like, the fix was there, and for a whole year, people's keys were at risk. So, if you remember, for this lattice attack for biased nonces, we always need at least 2 signatures to look at. So we're wondering, okay, but are there any keys out there that are using a small nonce? Because it looks like small nonces appear, but there's only one signature on the blockchain. So the lattice attack wouldn't catch them because we need two signatures. So we tried to actually just brute force. We already did some, like earlier we did this 32-bit brute force. That's something you can do on your laptop in a few hours. Now brute forcing the whole 64-bit space of nonces, that's a bit more interesting. But I really had great fun, like writing C code that does like very efficient data structures and filled up a machine with 3 terabyte RAM. So the idea is you do a pre-computation. So first you spend a few days writing a large table, actually 2 tables here, that allow you to then, when you have a concrete signature, more efficiently see, does this signature come from a 64-bit number? The code for that is online if you have a cluster in your basement and want to attack Bitcoin or Ethereum. It's still kind of slow. We still need like 10 seconds per signature. But yeah, in other words, if you have a bad implementation that uses 64-bit nonces, and I know that you're using that, then even a single signature will reveal the private key within like 10 seconds. But applying that to all 1 billion signatures is out of reach for the abilities that we have. So we ran this on just like a sample of 140,000 signatures. Conclusion was there weren't, but like we didn't find much more. Yeah.
Can you explain, like, why is it only 2 to the 39? Like, in what? Can you explain a little how you check the whole 2 to the 64 with only 2 to the 39?
So the idea is you take g times, well, you take the first 2 to the power of 39 multiples of g.
Okay.
And you put this in a hash table. Hash table means, in this case, I'm just using it's a 256-bit number each, but I'm actually just storing the last 64 bits, so it's small. And this was chosen just to fit in the RAM. If we had more RAM, we could use a large number there, and then this computation would be faster. And what we do then is we take the signature and we subtract, and let's see how that works. We take the signature, the R value. I repeatedly subtract 2 to the power of 19 times g. So basically, blackboard. So basically we have the full range, 64 bits. For these numbers here, I have a hash map, so I recognize the number if it fits in there. And then I start with any number, and I always jump like this much around, and until I hit that space, and I know how often I have to jump, so I know the multiple of 2 to the power of 39 that got me there. Then I'm in the hash table. The hash table doesn't tell me that discrete log yet, but I now know that it's like a multiple of g that is less than 2 to the 39, and then I can do a similar trick within the smaller space and use this lookup table to find the d-log. So I have basically make large steps until I'm in this area, then I make smaller steps until I'm in this area, and then I can look it up. If you want to see more details, we can maybe.
Yeah, I guess intuitively it's because there's a discrete log algorithm whose complexity is square root.
Precisely.
Sort of.
Yeah. There are like a bunch of them. Baby step, big step is I think, or colored row. Like this is like a pretty standard application of that. Like there's nothing very surprising here. Just was fun to do. Right. 2 more screw-ups to demonstrate. This one actually is SSH, not Bitcoin or Ethereum, but it's still fun, and I guess it could have happened there as well. We found signatures that had a shared 32-bit suffix. So there was randomness, but the last 32-bit were fixed. So we have this number here. So what do you do when you have a hex string and you want to know what it means? You Google for it. Didn't turn up much, but it turned up something. It was disassembled ARM binaries of just random like embedded systems and things. So I think I even found some of that in my own binaries on my laptop that was somehow related to crypto. And then I Googled again, but I changed the byte order. So I didn't Google for F2, 7, 8, and so on, but I Googled for C6, 7, 1, 7, 8, F2. And then I found this number in the specification for SHA-256. So this SHA-256 hash, when you want to calculate it, there's a number of constant words in the spec, and they somehow are, I don't know how SHA precisely works, but somehow they are mixed into the data, and there's some different rounds to be done, and you need to know these constants. And this constant is one of them. But I mean, this is just, like archaeology. Like, you get some piece of information, and you have to make assumptions what has happened here, or hypothesis. So it looks like somebody was trying to use a SHA hash to get a random nonce, which is not unreasonable. Using a cryptographic hash to get a random number, like if you seed it properly, well, it's a good way of doing it. But they must have screwed up the calculation of the SHA hash because now the last 8 bytes are always the same. Maybe they didn't do enough. Maybe they thought, oh, we don't need all the rounds or something. Very odd. Unfortunately, the SSH hosts were down. So the SSH keys that we looked at, there's basically a project called Census going on that's scanning the internet regularly for HTTPS and SSH hosts, and they're storing the key exchange. And then there's a database, and as a researcher, you can get access, and you can basically do a large amount of data checking of this key exchange. So we found this there, but by the time we found it, the hosts were no longer online. So we don't know what implementation did that wrong. So we couldn't notify anybody about it. And then the last one is my favorite one. We found a number of signatures that had a shared 128-bit suffix. So here's the nonce, and the nonce, like the last half of the nonce, was the same in all signatures for that secret key. And if you look more closely, you notice that the 128-bit that are same in the bottom of the nonce are actually the high bits of the secret key. That's what I thought, yeah. Oh. So how could that happen? So my best bet, and I'm a programming language nerd, I like Haskell, so obviously bashing C is precisely what I like to do. My best bet is somebody was using a memory unsafe language like C. And they maybe wrote code that roughly looks like that. So they have maybe on their stack or in the heap some buffers for K and for D, for the nonce and for the secret key. And maybe they even filled the space for the random nonce with the right 32 bytes of randomness. Remember, it's very important to write 32 here, not 8. So maybe they got that right. But then they copied the secret key into their working area, and maybe they just got the bounds wrong. Like, this buffer is too short for the amount of data they copy in, and this way the data overlaps the secret key, and yeah, that breaks. Now, this didn't reveal any interesting keys. The reason is that these keys, maybe you've seen it already, like there are 2 keys that actually, they're a short secret key. This is already unsafe. Like, you don't pick 11 as your secret key. That's not very secret. So all of these signatures were emptying out accounts of secret keys that were already leaked before. Short keys, example keys from tutorials, like, if you get some tutorial about ECDSA, there's an example key in the tutorial. For some reason, somebody tried to, I don't know why people would send money to such an address, but maybe they did, just to play around with it. Secret keys that are leaked because somebody was using a bad password for like a brain wallet key. Where you have something in your head, and if you use it too small of a text, then people just brute force these and crack them. So there was, all of these were emptying out leaked, the accounts of leaked private keys. So the theory here is, at least my theory is, that the code that is broken is the code that some attacker wrote to empty out people's accounts. I'm not sure what to make out of this revelation, but it's kind of nice to see bugs of attackers just by looking at the blockchain and thinking for a while. So this is what we found in terms of possible explanations of some of these. It doesn't explain all of them, and it's really hard to like find the real implementation to notify people. I guess the only one where we really found the cause was this bit pay thing, but that was already fixed. So it was more or less, yeah, unhelpful maybe. But still, it's a useful warning to everybody. Don't implement your own crypto. Don't mess up with your random number generator. And all of these problems could have been easily avoided by one small trick. And now it sounds like clickbait. But it is one small trick. Can't help it. You don't have to use a random number. You can instead get the random nonce by hashing, with a suitable hash, it's large enough, the secret key and the message hash, and use that. This is equally unpredictable as a random number, but it's not random. And that makes it much easier to get it right. And then all the problems like random number generators go away. Maybe not all the problems, like the memory unsafe stuff can still happen, but still, like at least you don't have to worry about getting randomness, which is often tricky. All the official clients already do that, and I guess I don't have it on this graph, but in the paper we can see that I think somewhere around here Bitcoin started, like the official Bitcoin SCP library started using deterministic nonces, and we can speculate that this drop of bad signatures corresponds to that, because now you don't need random number generator anymore, so a bad one doesn't affect you anymore. So if you use official libraries and clients, don't worry, this is being done correctly. If you use other signature schemes like ED25519, then they only support that, so it's built in, so that's safe.
But doesn't the hash require a random key to be, the H doesn't need a...
No, it could just be SHA-256.
And it doesn't need a key?
No. No, I mean, hashing is just a function that takes some data and spits out a number in a certain range from which you can't. And there's nothing secret about there, nothing that needs to be varied. I mean, that hacker doesn't know D, and by hashing D together with the message hash, you get a different number every time.
Isn't this in principle a bad idea, given the fact that there are no proofs that there aren't ways to accelerate reversing one-way functions in one way or another, so some probabilistic effects. So I know that there's no proof that there isn't a way to invert them, so why take the chance, right?
Because of this, and especially this.
I'm not saying you
like,
can mess everything up, but you're actually correlating things there in a way. I mean, I get it that for now you don't know how to quickly invert or probabilistically invert a one-way hash, but it doesn't mean it's impossible.
Right, but all crypto that we're using is built on optimistic assumptions that some things are hard.
I think what you're asking, the way, you're essentially asking, why trust any crypto at all? It can be broken at any time. So I'm with you. It's a dangerous world to trust current crypto, but maybe
we don't know. I mean, it's not like that means that it hasn't broken, but
it's not a bad comment, because, for example, you might be tempted to say, "Oh, I'll just I hope I get it right. I just XOR D and H," which also mixes them very nicely. And people have been using that, like, because they think, "Oh, I can just do that. It's cheaper than a real hash function." But Nadia is actually working. Oh, should it? Oh, never mind. I think people are trying to see if they can attack that. So that would be a too obvious correlation.
Yeah.
But I guess the hope is that we're building so much on the safety of SHA-256. So if there's some correlation that leaks through this very unlikely machinery of SHA-256 or some other hash function, then much more is at stake than just the safety of this. So I would go for the pragmatic thing and say it's much more likely to have a problem because your random numbers are predictable or something else goes wrong than that you can actually get a correlation between D and K in this scheme.
Through the hash.
Yeah, I mean, hashes are pretty reliable if you take the latest ones, maybe. And it's not like you're revealing K. K is still then encrypted with like K times G.
Yeah.
So you would have to have an attack like this where you find some correlation between the Ks that you can attack in like a linear manner, like what we did here with like subtraction and shifting around. Maybe I'm too optimistic. So it's certainly a good question. And it's interesting to see that I believe, and I'm just telling what I believe I picked up somewhere, is that when you try to formally prove security of signature schemes, based on some assumption like D-log is hard, then using this actually makes the proof much harder because precisely it's unclear if there is such correlation. It's just very implausible, maybe, that they are. But it is a valid concern, yeah.
Well, I actually have to find an article that I wrote and it was beautifully written where how to generate a crypto system that has an invertible one-way function without anyone else being able to find it. Right? That was the paper.
Okay.
It actually showed the methodology of doing that. So it doesn't mean that it happened. It doesn't mean that this is ruined. But as I said, maybe compounding even more predictability, just like this lattice analysis that you're bringing up, right? So it's not something you would have thought of at the beginning, and yet it can be used in this way. So if you compound more deterministic stuff on top, you're going towards less entropy, right? And doing something which is completely random. I get that you can mess that up, but...
Yeah, I guess maybe there's a tension between theoretical safeness and practical safeness, because most crypto attacks are not because the math was wrong or because you could suddenly invert some D-log. It's because people screw up implementations. And the easier you make it as a crypto designer for your scheme to be implemented correctly, the less things you put in that need to be carefully done by somebody who's not an expert, the more likely is it safe. But maybe it's a tension, I agree.
So the idea was actually to create a real 256-bit K. This was really the goal. And the assumption is that the hash is a good thing because if you are changing one bit in D, 128 bits are changed in K.
Correct. Yeah.
256 even, right?
Well, I guess half the bits are changing on average.
About half a bit.
No, in K, all 256, right? If you change one bit in D, the hash should completely change.
No, that would mean that
only
the
128 bits. Basically, you want 128 bits to change. If you are changing more, this means that other hashes are changing less.
To change them all would be to invert it, right? That's the only way you could change them.
Oh, yeah, they're saying 128 is, the maximum.
So if I change one bit, well, I guess it's hard to see which bits are changing. But it didn't even work. See, it's not going from 0 to F. It's going from 0 to C. So some bits change, some bits didn't change. Okay. So, yeah, please.
So the attack that you described is when the nonce is generated. Certainly if the nonces are low values with the 0 prefixes or 0 suffixes or shared prefixes, shared suffixes. If the randomness is a little bit more obscure than that, is there a practical attack? So suppose you picked nonces that were 64-bit numbers and then you hashed them and then those were your nonces. Would you be able, because the actual randomness is only 64 bits, would this attack be practical in some way or not so much?
So the way Nadia phrased it always is like any bias can be attacked. We just don't know yet how. I guess I'm a bit more naive here and say, well, if you really put them through a good hash, then probably no attack like this works because you still need some kind of regularity in the bias. Right. I'm not the crypto person, so I'm not the one to say, yes, you're safe.
I mean, if you knew somebody did that, you could try to brute force the 250
so, for example, like
hashes and then you could reverse it. But the practical question isn't like some procedure like that, but what usually happens is you have some random number generator that you think is secure, and but what if it's not actually perfectly uniform?
But at least for the hash functions, the assumption is that a hash function produces uniform output. So if you take one secret number and then you just count up by 1 for each signature you create, and you take hashes of that, I believe that's a valid implementation for a cryptographically secure random number generator. So maybe if there's hashes involved, it's fine. What I find more interesting is questions like, and people screw up and, for example, put not the hex number, like put not the binary data into the K, but rather the hex encoding in ASCII, because they use Python and types don't uncheck. And I'm a language nerd, so I look down on languages that don't separate between the hex representation of a byte string and the byte string itself. So what happens if your K is filling all the bytes, but all the bytes are ASCII numbers, 0 to 9 and 1 to F? Can this be attacked? And I guess this doesn't do it out of the box, but probably somebody who's clever can find an attack against these things.
So if out of the 256 bits, I'm selecting a kind of a random subset.
Mm-hmm.
This is similar to you. Mm-hmm. Did you check if you can find the... I want to put it more in the specific terms.
This is kind of similar to what I just described with like ASCII data in the thing, because there also some bits are always set because like the high bits in every byte, for example. So I wouldn't know how to do it off.
But you will not.
But I wouldn't be surprised if some trick along these lines, some clever multiplication addition will move the bias in like more compact regions, and then these attacks might work.
So there are no lattice attacks on random. There's some random number generators that have had lattice attacks on them, which sounds kind of like in the right sort of range of what you're talking about.
Okay.
To me, anyway.
Yeah. Yeah. I mean, I'm being because I wouldn't be surprised if you can make an attack that against like.
Yeah, I understand. I just was wondering if you were looking at in general subset or you looked at all structured subset.
We don't look at these cases. It's no fun looking for things if then in the end nothing is found. So looking for some very obscure patterns where it's not plausible that somebody screwed it up that way. Why do that?
But this is a very simple solution, because just by hashing, you are creating a subset of 256.
Well,
just by hash, if you're taking this 128 bits,
mm-hmm.
and you are just doing the hashing, you are getting 256 bits.
Yeah.
And a subset of 256,
Right, but if you're already thinking about this and just get it right initially and get a full 256 numbers. Or I guess it's what I was saying, if you properly hash it and the 228 bits are like chosen incrementally or something, I guess that's one way of implementing a random generator. So you're just doing your job of implementing a random number generator. Although it probably shouldn't be your job. Probably you should pick one that's out there and reliable.
Okay, it looked like you didn't quite make it to the end of your slide.
I did.
Oh, you did?
Yes, this was the last slide before the summary slide. So it was perfect timing. I have a copy of the paper with me. I don't need it anymore. So if anybody wants to read like more details, I'll just leave it here. Thanks for the attention and all the questions. It was fun. And
so I have one, maybe two final questions. Do you have any comments on, like, it didn't seem like any of the vulnerabilities that you specifically found were Ethereum specific, is that right? Or were there...
Right, so most of them are Bitcoin. I guess it's just because Bitcoin is bigger in terms of signature and older, and more people mess around with it that have less of a clue, I guess.
Oh. Okay, that's a positive comment.
That's a positive. That's very positive. I can try to recap what we had the numbers here. There was just much less on Ethereum, I guess that's maybe Ethereum is more complicated, so people are more likely to use the official client rather than build their own.
Okay.
That could be. So here we had three. Yeah, I can look at it in the paper real quick. What we found. Right, there's a section on that. So we found. Well, there was, one key compromise that was using a random, that had like a fixed prefix of 192 bits, and then random 64 bits in the end. And there were 7 signatures from this key. 2 looked fine, like completely random, and the other 5 had this property. Like, we could have taken 0.0002 ether from there. So this was one instance of biased nonces. And then there were like 3 keys compromised from repeated nonces. There were nonces 1, so obviously test. There was nonce 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Also looks like a test nonce. And then 1 that looked like a random nonce. And all these were empty. So I guess people, it's reasonable. People play around with, write their own code. People craft their own transactions. As long as you do that with not real money, nothing, can't complain about that.
So I'm curious, it may not be reasonable for everybody to go off and run the 50 core year sort of computation, but that was on the entire blockchain for not just Ethereum, but Bitcoin, Ethereum, Ripple, lots of HTTPS and SSH keys, maybe on GitHub. But I'm just wondering if I'm right that one could write a tool that was specific, say, to Ethereum, which you could say, all right, go check and see the transactions associated with this address, and kind of check my own. I just want to see if my addresses that I've been using here is doing anything stupid, or if this exchange that I'm thinking about using are doing anything stupid. I mean, is that a tool that could be written? Or, for example, somebody who has could make this a service. Somebody who's wants to do some startup, they could sell the service of watching your addresses and telling you of something.
They could even do it like in the old style, like you provide the service, and if you're not paying for it, then they take the money out of your account.
I'm actually not suggesting that. That's not.
Well, that can be fixed in marketing.
I mean, it's just a question of incentive, isn't it? No, more serious. Yeah, you could do that. I'm not sure how useful it is, because if you're already thinking about it, then the best way of avoiding all these problems is just use the official client.
Well, though actually, what I was thinking. Well, you're right, but if you want to play around with things, and it's possible to do something stupid, I guess, if on the one hand, you don't ever want to write your own crypto, right? That's the whole point, is you don't ever want to roll your own crypto, but nevertheless, you want to play around with it. So these are intention, how do you get the people to learn crypto? So if you have the tool to kind of watch some transactions and make certain that there's a tool that's trusted. Anyway, I was just imagining.
No, it's not a bad idea. I guess could be part of a more general linting tool that just warns you about bad stuff. I mean, there's probably other stuff you can do wrong that you can detect on the chain.
Build it in a wallet. The miners are the ones that are positioned best to do it because they have the processing power.
Well, they wanted to use it for something else.
And they can provide the services also.
Okay, yeah, so someone could provide the service. Okay.
Yeah. But really, if you're targeting one particular public key, then this is not much compute power needed.
Okay, so
this could be something you just install locally and say, okay, now please check these keys for obvious vulnerabilities. Okay. Might be a fun project for somebody, yeah.
Okay, so let's see, Steve. Any quick questions?
A random comment. Given that you saw the 13337 and stuff, I love the idea of using like mistaken cryptography as a form of censorship-resistant steganography.
Well, people put stuff on the Bitcoin blockchain anyway that you don't necessarily want to have on your laptop anyway. It's like the idea of hiding stuff in the blockchain is not new. You don't need to do it that.
Yeah, no, I mean,
but
put state in the blockchain any which way. It's like, steganography is like where you're not really encrypting something, but you're putting things in places where people might not notice them for a long time.
I thought I'm not sure where I got that from. So maybe I'm spreading rumors that I just made up myself. But I thought there were people actually using the nonce on Bitcoin to like command botnets. But if the receiver of the message has the private key, they can also calculate the nonce, I believe. And it's a random value that changes every time that is not easily readable from anybody else. So it's a very good place to hide a piece of information. So yeah, I guess people do that already. Unfortunately, not the nice people, but yeah.
That's an interesting, I mean, what kind of application, given that you can't, that arbitrarily nonces you don't have attacks for, they might exist, but so if it's the case that you can, smuggle interesting information through tweaking random bits of nonsense that nobody gets to see, that's kind of an interesting meta secure messaging system or something.
Yeah, and the receiver just needs to know the secret key and they can get it again, and they know what to look for. So, yeah.
Okay, that's fun.
You can have a system with 4 commands.
I have a
You're
question.
checking before 4K.
Have you thought about
Stays there.
using this,
Sure.
performing this on the test nets? Because people are screwing around more and just do statistical analyses on the ideas that people are playing with.
No, we didn't. That's a good idea. I mean, it's less impressive to say we found a bug on the testnet, but we maybe would have found more interesting data, and maybe it's even much. I guess the testnet is much smaller, I would assume, in terms of size of the chain, because this is just always big. Like catching up with the Ethereum node is annoying. So maybe there would have been more. Yeah, good idea. Thank you. I'll relay it.
Okay, hopefully you guys are done with the questions. I think that you'll still stick around for at least a few minutes. Do you need to leave soon? Anyway,
yeah.
I think we will close with the formal part of the event. Thank you very much.
Yeah.
Great pleasure.